by both Neil Dixon and Blair Holloway from WFO Charleston, South Carolina. Should be some very interesting topics discussed today. I think we were going to do Neil. Were you going to go first, or Blair? Did you have a preference this morning?
Yeah, I can go first.
Okay, so Neil, you were going to be speaking about the effects of ship-induced Bernoulli wakes on the Savannah River in Georgia. So feel free to take it away when you're ready.
All right, I'll see if I can put this in presentation mode. All right, I'm just working with one screen. Does it show up okay, my title slide?
I can see and hear you. Yes, see the slides, all good.
Okay, well, I'll get started. Yeah, good morning, everyone. Again, my name is Neil Dixon. I'm one of the forecasters at the Weather Service office in Charleston, South Carolina. And we have two coastal sites that we produce coastal flood advisories and warnings for. One is in the Charleston Harbor, and the other one's on the Savannah River. The Savannah River is interesting because it has a lot of ship traffic that passes right by the tide gauge. So that's what we're going to be talking about this morning. The Port of Savannah is one of the fastest growing ports in all of the United States, and it's already the fourth busiest port in the nation. Pre-pandemic, it was receiving 36 weekly vessel calls, and it's one of the largest, if not the largest, single container terminals on the U.S. East Coast, if not the United States. As far as exporting is concerned, I was able to find some data, and the Los Angeles terminal is in the lead with 17 million tons of containers being exported from the port. But you can see Savannah's in second place at a little over 13 million tons. So just to give you a little bit of the lay of the land, the Savannah terminal is located about 18 miles from the coast, from the Atlantic Ocean, up the Savannah River, north of the city of Savannah. So you can see it up here. The ships take this journey kind of winding through the Savannah River and then pass by the Savannah Harbor Pilot's Dock, which is located near the mouth of the Savannah River. And in this box is blown up, you can see the actual Coast Guard dock and then the Harbor Pilot dock. And this is where the Fort Pulaski tide gauge is located. It's on this dock. But the ship wakes have been an issue on the Savannah River for quite some time, to the point that they've assigned 3 different areas where the ship's speeds are actually limited. One of them is right at the Coast Guard dock. There's another one about midway up journey by this fuel depot. And then the longest area where the speed is limited is passing right by the city of Savannah. Again, the tide gauge is located at the Harbor Pilot Dock, which is positioned about 240 feet from the shore at an average or at a depth of 17 feet mean low water. The center of the shipping channel is about 580 feet from the tide gauge, and the channel itself at the tide gauge is roughly about 215 feet in width. So every year, hundreds of ships are arriving at the terminal and departing from the terminal. And each time those ships pass by, there's a phenomenon called a Bernoulli wake. And that's where the water actually recedes for a period of time, roughly about 80 seconds. And then it's followed by a surge wave. And this whole process can go on for about 6.5 minutes. So I have a video. I'm going to have to bail out of PowerPoint and play it online. So let's see how this works out.
Can you, Neil, also hide that little message about sharing your screen.
Oh, okay.
Great. Thank you.
Yeah. All right. So can everybody see this YouTube video?
Yes, we can.
All right. So this is taken from the Columbia River all the way over in Washington State. And these Bernoulli wakes, occur anywhere where there's large ships passing by. So they occur worldwide. There's nothing special about the Savannah River. And in this video, let me pause it for just a second. You can see kind of a standardized or standard size container ship is about to pass by. You can see kind of like it looks like a bridge abutment over on the left and some sort of little concrete structure that's in the water. But as the ship is passing by, you can see the Bernoulli wake begin to form with the water receding right along the shoreline. So just, kind of watch these rocks as the ship is passing. So the ship is displacing water, which is equivalent to its cargo or its total tonnage. And as the ship moves, that water displacement is moving with it. So the water being displaced is equivalent. And as the ship is moving, the water is going to have to follow the ship. So it's receding at this point, as you see in the video. And you can check out this rock. Soon it will become totally exposed because this water you can see the water is draining away. Then as soon as the ship passes, then you receive this first surge wave. And this is not like a typical oscillating wave that you see, with boats. We're all, familiar with those type of waves. It's kind of like a little mini tsunami. And this water just surges in and it's creating a real water level change on the river. Now, granted, this water level change is going to be temporary, but it will last, for several minutes, if not as long as 6.5 minutes. So you'll see these surges kind of come in and out, and then eventually the oscillating waves associated with the ship actually breaking the water and creating waves, they'll make it to shore. But this surging back and forth will take place for a few more minutes. I won't play this whole video just to, for the sake of time, but it gives you a good idea of what's going on. And it's ironic that the title of this video is "A Freighter on the Columbia River Causing Shoreline Water Level Drop." Why? Because it is kind of an odd phenomenon. So I'll go back to my PowerPoint presentation. All right. So in this study, I recorded the 1 minute and the 6 minute water level data at the Fort Pulaski tide gauge. And again, that Fort Pulaski tide gauge is representative tide gauge for all of our Charleston coast and a portion of the southern South Carolina coast. And I did this for the passage of 113 ships. And they ranged anywhere from the standard size ship, like you see in the picture here, to kind of these recently arriving Neo-Panamax vessels, which started to arrive in Savannah and the Charleston Harbor about 3 years ago. These are the largest ships. And I did this from a period from late October of 2018 through the majority of March of 2019. So I broke these ships down. These are kind of standardized dimensions for these types of ships. You have the early container. You have what's called these fully cellular ships. These are commonly called Rolo ships. They're basically like floating parking garages. So these are pretty common here because we have the Volvo plant, the BMW plant. So these are importing and exporting vehicles from the port. So I was only able to capture 3 of these early container ships, mainly because they seem to be getting phased out. They're much smaller and older. The Savannah Terminal is not as busy with the automotive exporting and importing as like the Brunswick Terminal, which is just down the coastline. So that's probably why I only was able to capture about 8 of these vessels. The bread and butter of the Savannah Terminal is these container ships. So you have the older Panamax, which are as long as 275 meters. They're 32 meters in width, and they sit in the water 12.5 meters. So I was able to capture 31. But the most popular dimensions of the ships were the post-Panamax. Witnessed 46 of these ships, and these are as long as 335 meters in length, 40 meters in width, and have a draft of 13 meters. And then the largest vessels, these Neo-Panamax, they're 366 meters, so they're roughly like 1,200 feet in length. They're 49 meters in width and have a draft of over 15 meters. So I was able to capture 12 of those. So a good little sampling of all the different types of vessels that arrive at the Savannah Terminal. And then I used this free website called Marine Traffic. I was able to get the vessel's position, the water displacement, which is basically the tonnage of the vessel, the length, the width, the draught, and the speed. So all these parameters were all collected in near real time using the Marine Traffic website. And then using the marine traffic information and then comparing it with the tide data, over here you see this is the 6-minute data, which is what we use to verify our coastal flood advisories and warnings. And then to the right is the 1-minute data. So I was able to categorize those as the difference between the 1-minute high and low water levels. I did the same thing in the 6-minute data. And then in the 1-minute data, there was enough, it was high enough in resolution that I could actually take the water level before the ship's passage and find the peak, the absolute peak water level in the 1-minute data. So then I created a correlation coefficient to study the relationship between the water levels in the ships. I used the water displacement, the ship's length, the width, the draught, the speed. I actually calculated a general Froude number, a length Froude, a blocking coefficient, and the speed of the ships. But all in all, basically the best correlation was with the ship's length and width, which was very handy because basically these ships, the dimensions of the length and width are basically the same ratio. So it falls very nicely in the vessel types. So after looking at 113 ships, was basically able to observe that the larger ships resulted in a greater change in the water levels in both the 1-minute and the 6-minute data. The 6-minute data was less impacted by these Bernoulli weights simply because they're just kind of an average measurement of the water level over a 6-minute period. So there was more, I guess, diversity in the water level changes in the 1-minute data. And this, but the 6-minute data was still long enough that it was able to capture the entire duration of these ship wakes, because another study found that they last about 6.5 minutes. And then that solitary trough, that water drawdown as a ship's passage, was to be around 80 seconds. And that makes sense because some of these longer ships are about 1,200 feet. And if they're moving at about 13 feet per second upstream, then that's going to last anywhere from a minute to a minute and a half. And then another interesting part was I looked at the historical coastal flood events, and using our database from 1997 to 2018, there were 234 historic flooding events. And that was at using our old criteria of 9.2 feet mean lower low water in the 6-minute data. And out of those 234 events, 88 events, or roughly 38% of these flooding events, were actually augmented by the ship passage. So the passage of the ship was actually able to increase the water levels from what their natural tide would have been. And this also included 2 of the top 10 Fort Pulaski crests. And there were 20 flooding events, or 8.5%, that were a direct result of ship-induced Bernoulli wakes. And there's an example of one of these cases to the right. You can see that the natural water level curve would have crested just below the 9.2 foot flood stage. But that Bernoulli wake and the surge wave was able to increase the water levels just slightly above the 9.2. So this is one of those flooding events that was a direct result of the ship wake itself. And for this year, we only have one event at Fort Pulaski using our new flood stage of 9.5 feet. There's only one certified water level event from this year, and you can see that that was actually augmented by a ship wake itself, cresting at 9.65 feet. So in summary, basically the correlation coefficient indicated that the ship length and width had the greatest correlation between the 1 minute and the 6 minute data. And the 6 minute data was less impacted by these Bernoulli wakes than the 1 minute data. But that makes sense just given the longer duration of the 6 minute data. And the passage of these 113 ships showed that there is a relationship between the size of the ship and the magnitude of the water level changes. And generally, those larger ships are going to result in a greater change in water levels. So there's a question, what do you do with this information? Do you factor it in when you're doing your total water forecast? And, we're not doing that. We're just being aware that, yes, these ships do have an impact on the water levels, and we've seen these spikes in the past, and now we know that those are a direct result of the ship wakes themselves. So it kind of explains why we're seeing these little gyrations in the water level data, but it's going to be an issue as the port has plans to expand, and the ship traffic is just going to go up, especially once things get back to normal after the pandemic. So we're going to be seeing these changes more and more frequently. That concludes my segment of the presentation today. And here's my references and a little disclaimer about using the marine traffic webpage. So I will exit out of this and in my presentation mode.
Neil, thank you so much for that really interesting talk. I guess we have a couple of minutes for questions to budget for time. I see Jeff, you have your hand raised. Go ahead.
Yeah, Neil, well, thanks. Very interesting presentation. I was wondering, with at least what seems to me a fairly lengthy inland route that these ships have to take, 18 miles up to the port. Does that estuary require periodic dredging activities to maintain clearance from the bottom, or is it plenty deep enough?
Yes, I believe they're actively dredging the shipping channel right now, and these ship wakes are associated with pretty heavy erosion, both on the shoreline and below the water level. So one of the reasons that they have these speed limits on the channel is just to eliminate the amount of silting that's piling up in the shipping channel, because the more and more of these ship wakes, the faster the shipping channel will begin to shallow.
That makes sense. Thanks.
Ron, you have your hand raised as well. Go ahead.
Hey, good morning, everyone. Neil, excellent presentation. I always learn something, even though I've seen some of this before. I also wanted to let everybody know, too, that these wakes cause hazard on the beach on Tybee Island, which is the island just south of the shipping channel, south of the Savannah River there. And as you saw, they act as little mini tsunamis. And we had a video a while back that somebody shared of people being in the water and then being kind of swept out as first the wave came in and then it had a very strong current out. So just wanted to bring up that it also has some beach hazard to it as well.
Okay. Any other questions for Neil? I have one, but Jeff sort of took it away. If that's okay. Any other questions? If not, I'm hearing none. We'll move on to our second portion of the science sharing webinar edition this morning. That is a talk by Blair Holloway. The subject matter at hand is the operational implementation of a tide forecast tool for the Southeast Georgia and Southeast South Carolina coast. Blair, when you're ready, feel free to take it away.
All right, thank you. Let me do the present here. Let's see. Hang on one second. All right. Now, 1 second. Apparently my preferences are not allowing me to share here. Why?
Are you on a Mac or a Windows PC?
A Mac.
Okay, I'm less familiar with that. Let's see.
Blair, you can share your presentation with me and I can play them on my end.
Hang on 1 second. Let me try this one more time. Why is this not share? Huh.
I'm going to try to change a setting on my end that might help. Let me see if this fixes that. I just changed a setting, so feel free to try to share again and see what happens on the bottom.
Yeah, there's something with the system preferences, but I don't know.
It may be worth trying a different browser if something's locked in to like remember a setting like don't share screen. Maybe it's different on a different browser.
Okay, let me try that here real quick. All right, let me see. Can anybody see?
Well, we see that your screen is shared. That I can confirm.
Okay, hang on.
Okay, now I can see your slides.
think you're muted.
Okay, can you see the slides now? I'm sorry.
Yeah, we can see them right now. If you can't get into present mode, feel free to drive it. Oh, all right.
All right, there we go.
We're good. We're good to go. You have the floor, Blair.
Oh, thank goodness. Okay. All right, well, let's get started. Sorry about the technological snafus there. Yeah, like you said, I'm one of the lead forecasters here, and I'm going to talk about operational implementation of a tide forecast tool for our coast. Just a very brief outline. I'm going to go through a bit of the project background and kind of the original idea, where that came from. And then I will speak mostly about what we did locally to kind of adapt that original tool. Take a look at the research results, and then we'll take a look at some results from a recent event. First thing I'm going to start off with is just to kind of talk about the increasing nature of coastal flooding that we're seeing, not only, I'm sure, at our sites, in our CWA, but I'm sure that at other coastal sites as well. So this is just a plot of coastal flood events by year across the 99-year history available at the Charleston Harbor National Ocean Service tide gauge. And as you can see, it's obvious that we have a clear increasing trend. And so this really gets back to the importance of the total water level forecast that we produce on a daily basis. And I think it's good to kind of underscore what we're seeing, especially with the growth of coastal flooding, in that just in the last 2 years, 2019 and 2020, we had the same number, essentially the same number of coastal flood events as we did across the first 60 years of the history of this tide gauge. So kind of speaks to the importance of the total water level forecast and underscores the importance of the tool that we've developed here. So a little background about the project and where this idea came from. The forecast tool originated with the master's thesis of a graduate student from the College of Charleston, Joey Cause, back in 2019. That work has since been published in the Journal of Applied Meteorology and Climatology back in July of this year. And that project was led in part by Frank Alzheimer, the science officer at WFO Columbia. The project explored the correlation between the low tide tidal departure and then the high tide, the subsequent high tide tidal departure for the Charleston Harbor tide gauge. You can see on the right here with the image what I'm talking about. So kind of finding the relationship between this tidal departure at low tide and at high tide and seeing if the two were related in some way. And the idea being that could the low tide tidal departure be used to predict the high tide tidal departure and the subsequent high tide peak value. The project looked at or considered all coastal flood events from the 1996 to 2014 time period there in Charleston. And then the coastal flood events were assigned a synoptic category for one of 5 different categories: anticyclonic, cyclonic, frontal, neutral events, and then tropical events. And after these were divided or assigned categories, regression analysis was performed to develop forecast equations. And I'll talk a little bit more about it in a few minutes, but the tropical events were removed from consideration for the actual analysis. And the idea was that a forecaster, when making a tide forecast, could identify the event type and then use that particular equation to predict the peak value of the upcoming high tide. So that work really had a lot of promise and showed some good results. So we decided to set up our own project to essentially expand on this, the original Joey Cause work from 2019. We started in the fall of 2019, and we made it a student volunteer project with 2 students from the College of Charleston's meteorology program. We had a few different things that we wanted to do with the project. The first step was to update the Charleston Harbor data set to include events up to 2018. And this was important because we had 427 events from 1996 to 2014, or an average of just over 22 events per year. But as you remember from the very first graphic there, we've had a real explosion in the number of events just in the last few years. And so if you look at the 2015 to 2018 time period, we averaged just over 50 events a year. So twice as many as we did for the original data set. And to kind of underscore that point, through 2014, 42 events in a year was actually the annual maximum. And then from 2015 to 2018, 42 events in a year was actually the minimum across that time period. So a real increase in the number of events that would be used in the actual analysis. Step 2 would be to expand the project to Fort Pulaski. So to kind of start from scratch there and develop the same tide forecast tool. Step 3 was to use the 2019 and 2020 coastal flood event seasons to evaluate the accuracy of the regression equations. And those were 2 excellent years to use because those are now the 2 the number 1 and number 2 years on record. And then finally, the hope was to implement this into operations and use in our total water level forecasts. And the map on the right just shows, what our CWA looks like, and you can get a sense of where the 2 tide gauges are. And these are our 2 total water level forecast points as well. So for that 1996 to 2018 time period, we documented what you see on the right there for each coastal flood event at Charleston and at Fort Pulaski. So we found 628 events at Charleston and 236 events at Fort Pulaski. And for each one, we documented the observed peak tide value, the astronomical peak tide value, and then the subsequent high tide departure. And then for the low tide, what the observed low tide value was, and the astronomical low tide value, and calculated the low tide departure. We did the same thing as the cause work. We went through and assigned synoptic categories to each event, and then we tested the resulting equations for coastal flood events from 2019 and 2020. So we'll start with the Charleston Harbor data set. Like I said, we identified 628 events from 1996 to 2018. And an event constituted a peak observed tide of 7 feet mean low water or higher. That's basically our minor flood stage, and that's the point at which we began issuing coastal flood advisories. Looking at the synoptic category breakdown for these events, about 40% were classified as anticyclonic, about 20% each for the cyclonic and frontal categories, 10% for the neutral events, and then about 8% were classified as being tropical. We created scatter plots for all of the non-tropical events. Like I said, we removed the tropical events from consideration, and we used a quadratic fit for the regression equations, mainly because in both cases, the R squared value ended up being slightly higher for the quadratic versus a linear. All right, so here's a look at the data for the Charleston Harbor site. So we had 579 non-tropical coastal flood events, and those are shown in the scatter plot there on top. And you can see a relatively high R squared value. And just as a reminder, R squared is the coefficient of determination and is used to help quantify the strength of a relationship between 2 different variables. So a perfect relationship would give you an R squared of 1. So in this case, having an R squared of about 0.73 is actually really good. And looking at the R squared for each of the synoptic categories, you can see those in the second graph there on the bottom. R squared varied anywhere from about 0.76 for the frontal events all the way down to the lowest, which was 0.55 for the neutral events. So taking a look at the, using the 2019 and 2020 events as a test, For that time period, we had 157 total coastal flood events. We had similar kind of breakdown of category types as we did to the events that were used in the analysis. About 6% were tropical events, and those were removed for consideration here. But we calculated the mean absolute error for each using the category-specific equations and the all-inclusive equation as well. And if you look at those across the different category types, basically very little, if any, difference in the overall accuracy and the performance of the equations for those events. And looking at it on average, they're basically the same. Really very minimal differences between the performance for the category-specific equations and the all-inclusive equation. And if you break it down ever so slightly, you could say just in this particular test case that the all-inclusive equation was slightly more accurate, but very minimal difference overall. So if we break that down a little further and we kind of look at how these fit into different range bins based on the MAE. For the events with basically less than a tenth of a foot of MAE, about 40% for both the category specific and the all-inclusive equations. And then for those within basically 2/10 of a foot, again, very similar, 68% or 69%, depending on whether it was the category specific or the all-inclusive. So, overall, most of the time, they both perform very well, and really the performance is very similar, if not the same. But you can still get large errors. You can see looking for errors of basically 4/10 of a foot or higher. You're looking at anywhere around 7% or so of events. So it's not perfect all the time, but the majority of the time it does perform really well. All right, so that's the data for Fort Pulaski, or excuse me, for Charleston. So now if we take a look at Fort Pulaski, we followed the same process that we did at Charleston. However, a couple of things that we need to keep in mind when looking at the Fort Pulaski data and what we kind of modifications that we had to make as well. Like Neil just presented about, Fort Pulaski is very susceptible to these ship-induced Bernoulli wakes, both at high tide and at low tide. And that's significant because it can impact the peak tide value that occurs, and it can have significant impacts on the tidal departures that are calculated. And since that's what we're using, these tidal departures, what we're using for our relationship, that's a significant thing that needs to be accounted for. Kind of what we ended up doing was, if you're familiar with the National Ocean Service data sets, they have the 6-minute data, but then they also have this high-low data set. And I've emailed with them before to kind of get more information about it, but these high-low data sets where it actually performs some kind of filtering of the data. And so in the cases where the Bernoulli wakes were being observed, either at low tide or at high tide, we used the NOS's high-low data set to remove that effect. Similar to Neil's data, I was able to find about 35% of events in the data set had Bernoulli wakes at high tide, and then a slightly lower amount, but still significant, about 20% or so at low tide. And one other thing to keep in mind, when we started the project, our coastal flood threshold was 9.2 feet above mean lower low water, and that was increased in May of 2020 to 9.5 feet. That was through collaboration with Chatham County and folks from the city of Savannah to kind of better reflect where flooding, at what level flooding begins. So we increased that threshold. But for the purposes of the study, we continued to look at events that were 9.2 feet or higher. And that's what we continue to do to this day. All right, so Fort Pulaski, over that 1996 to 2018 period, we identified 236 events of 9.2 feet or higher. and you can see the breakdown of how that those synoptic categories were assigned. About 45% were anticyclonic, 20% each to cyclonic and frontal events, about 8% for neutral, and about 6% were considered to be tropical. And then just like we did at Charleston, we created these scatter plots for the non-tropical events. On the x-axis, we put the low tide departure, or what we and the cause work called the delta low, and then on the y-axis was the high tide departure, or delta high. And same breakdown, we have the all of the non-tropical events in the graph on top, of which we had 222, and then we have the category breakdown in the second graph there on the bottom. So the first thing that should jump out is that the R squared was significantly lower than it was at Charleston, so just shy of 0.5 for all the non-tropical events. And then looking across the different categories, that ranged anywhere from a high of 0.55 for the frontal events, all the way down to about 0.43 for the cyclonic events. All right, and the same kind of analysis as far as the performance goes using the mean absolute error. Again, using 2019 and 2020 as our test case, we had identified 80 different coastal flood events during that time period. And that broke down to about half of those being anticyclonic, 20% being cyclonic, 10% each for the frontal and the neutral events, and then just shy of 10% for the coastal, or excuse me, for the tropical events. Again, just like we saw in the R squared, the mean absolute error is noticeably higher here than it was at Charleston. So you're looking at anywhere, roughly around 0.2 to 1/4 of a foot, depending on the different category. But again, we kind of see the same idea that the MAE is very similar, whether you're using the category-specific equations or the all-inclusive equation and looking at the mean absolute error. So not much difference there. So kind of the same takeaway that overall you're not getting much difference there, and you're not seeing much of an improvement using the category-specific equations. As expected, when we break it down into the range bins, the data is not quite as good as it was at Charleston. So for events that were within 1/10 of a foot, it only occurred about 22% of the time for both the category specific and the all-inclusive equations. And for having an MAE within 0.2, you're about 45 to 50% of the time, whether it was the category specific or the all-inclusive there. So not nearly as accurate as it was for the Charleston Harbor data. And also, it produces the larger errors, so basically 0.4 of a foot or higher, about twice as frequently. So about 14% of events for Fort Pulaski compared to 7% at Charleston. Okay, so just a few summary things from the research that we've seen. The tool appears to perform very well overall for the Charleston Harbor site, but this performance is considerably less at Fort Pulaski. Overall, at both sites, the very minimal difference in the accuracy of the category-specific equations and the all-inclusive equations. So really no difference, significant difference between the two. Just some things that we noticed looking at events from the database. The tool seems to perform best when conditions are basically steady state from the low tide all the way up through the upcoming high tide. Tended to notice larger errors as you were kind of coming into and coming out of multi-day coastal flood events. But really it does best when there's no significant change in the ambient meteorological conditions from low tide to high tide. That's when the tool really seems to perform best. And if you want to read even more about the nitty-gritty of this, the work has been accepted for publication in the NWA's Journal of Operational Meteorology and should be available sometime soon. Okay, so the last step of what we hope to accomplish with our project is implementing this operationally. And I think with a lot of different, really any tool that you try to get into operations, it needs to be something that's relatively fast, simple, and easy to access for the forecasters. To do this, we decided to just use the all-inclusive regression equation and not mess with the category-specific ones. We thought this would simplify the process for forecasters when preparing total water level forecasts. It really just prevents the forecaster from having to identify whatever the ongoing synoptic category type is and then selecting the appropriate category equation. It's easy. I mean, you only really need two inputs. You just need to wait for the low tide to occur so that you can calculate your low tide departure. And then you also had to input whatever the upcoming astronomical high tide value is. Do those two things and you'll get your forecast for the upcoming high tide. Since we've only included events that were in excess of 7 feet in Charleston and 9.2 feet at Fort Pulaski, it's really only meant for use when we're looking at tides of that value. So, basically looking at flooding tides is what it's meant to be used for. Some, kind of limitations, I guess, is the lead time. It really is limited to just about 6 hours, which is the time period between low and high tide for us. So you need that observed low tide to occur so that you can calculate the departure to do the actual forecast calculation. So you can only do that about 6 hours prior to the upcoming high tide, which means that the use of the tool is primarily to tweak our total water level forecast for the upcoming high tide. And the idea is that could then assist with whether we need to issue coastal flood advisories, or if we have, say, a watch that's in place, do we need to go to a warning, or can we just keep the advisory as it is? Not meant to be used during tropical events. Obviously tropical events are very complex when you're dealing with, especially significant storm surge. And, including these in the analysis, you're talking about tropical events that produce extremely large tidal departures in some cases. And that could mean that you have a relatively small number of events that have, kind of an outsized impact on the statistical relationship derived when looking at the delta low and the delta high. When we first started using the tool, it was based just in Google Sheets, and the forecasters could go in and put their inputs in and get the forecast. But just recently, our total water level focal point has made this something that is automatically calculated on a web page. So it makes it even easier for forecasters to use. And one thing that I think would be interesting to see is, can this tool and this method be useful at other sites along the coast, whether that's other Eastern region sites or, Gulf sites, wherever. And it would be interesting to see if it has utility for total water level forecasts at other Eastern region offices. All right, the last thing I'll show before I wrap things up is some recent performance from the tool. We had a pretty significant multi-day coastal flood event that took place from November 3rd through November 11th. Looking at that, at Charleston Harbor, we had 10 individual tides of 7 feet or higher. That's now the most for any November on record. And we also had 4 tides of 8 feet or higher. 8 feet is our major flood stage. So that's the point at which we issue coastal flood warnings. And those 4 tides, that's the most for any month on record, the third most for any year on record. And then we also had three of the top 15 tides on record as well. So a pretty significant multi-day event. And at Charleston, it really did, the forecast tool really did a great job overall. The mean absolute error for those 10 7-foot tides was just 0.1 feet. And then for 6 of the 10, the tide tool error was within 0.08 of a foot. So in some cases, nearly a totally perfect forecast. Looking at Fort Pulaski, we had 6 tides of 9.5 feet. Remember, that's the new threshold for coastal flooding and issuing coastal flood advisories. That's the most now for any November on record, and just fell short of being the most for any month on record, period. And data at Fort Pulaski goes back to 1936. We also had 3 tides of 10 feet or higher, and that's the moderate flood stage. That was one of the changes that we made. 10 feet used to be the major flood stage at Fort Pulaski, and we adjusted the levels back in May of 2020. 10 feet is now the moderate flood level at Fort Pulaski. So that having those 3 10-foot tides, that's tied for the most of any month and year on record. And we also had 2 of the top 11 tides on record, including the 4th highest on record and what's now the highest non-tropical tide on record. So overall, the forecast tool for Fort Pulaski didn't perform quite as well, but kind of in line with the data that we saw when developing the tool. The mean absolute error for all 6 of the 9.5-foot tides was 0.27 feet. But there really were a few that it was almost completely perfect. So for 2 of those 6, the tide tool error was just 0.03 of a foot, and then just 1/100th of a foot. And some of that data is skewed by, there was one particular tide where the tool was off by about 3/4 of a foot. And so that really kind of skewed the data a little bit there. And that was a case where locally the winds were kind of tipping from more like north-northeast to become kind of more north-northwest or even northwest, which is a less optimal wind direction. But still, it provided at least some benefit, I feel like, for the forecasters. All right, and that is everything that I have here today for this. I'll take any questions if there are any.
All right, Blair. Well, thank you very much for that. Another very interesting presentation. I am actually going to start off with a question of my own to kick off the question session here. So on one of your earlier slides, it seemed like, you had the R-squared value correlation values for, Charleston versus Fort Pulaski. One of my points of curiosity is whether or not the R-squared values correlate to flow orientation specifically, or if it's more flow magnitude, or is it a combination of both?
Yeah, we didn't look at that specifically. I think you see some of that, when looking at the different categories. So typically, like for these anticyclonic events, you're getting usually getting northeast wind along the coast, which is what drives our tidal departures to be really high. And obviously, they're even higher if it's not only northeast flow, but if it's strong northeast flow. And so you see some of that, I think, for instance, like with the Charleston data, the neutral events had the lowest kind of R-squared values. And then at Fort Pulaski, I guess you kind of see that a little bit too. One thing that I've wondered about as well is kind of figuring out why maybe you don't see that same strength of relationship at Pulaski as you do at Charleston Harbor. I'll show this map here. It may not be quite big enough, but if you look at where Charleston Harbor is sited, it's right here on the east side of the Charleston Peninsula, and it's kind of contained within this protected, Charleston Harbor area here. There's a couple of freshwater rivers that empty into the harbor as well. But if you contrast that with what you see at Fort Pulaski, it's a totally different, kind of coastal geographic setup. At Fort Pulaski, the tide gauge is right here, basically right at the mouth of the Savannah River where it empties into the Atlantic Ocean. But it's not a protected harbor. It's just, you know, basically sited right there at the end of the river. So I've kind of wondered if there's some differences there just based on, you know, kind of the shape and orientation of the coastline with where these two sites are.
All right, thanks. Appreciate the response.
Sure.
Are there any other questions for Blair? Jeff, I see you have your hand raised. Go ahead.
Hey, Blair. Great presentation. Just wondering, for the November case at Fort Pulaski, were there any Bernoulli wake events that could have impacted what the observed tides were?
Surprisingly, no. All the flooding tides, the tide trace was very smooth, and there was no noticeable impact for any of the flooding tides from the ship activity and the associated wakes.
Thanks.
Ron, go ahead.
Hey, thanks, Blair. Excellent presentation. I guess my question for comparing this to our recent event, would we have actually expected that tool to do very well? I don't know. Would we consider that event to be a sort of a steady state event? I mean, it was a chain of lows kind of periodically traversing offshore. We had probably fluctuating northeast wind speeds plus change in direction. So I was surprised that actually your numbers were as good as they were with an event that really wasn't steady state in my mind.
Yeah, I think looking back on it, it really was pretty steady state. And I think some of it, you know, whereas, and I just say I worked the event and I actually found it kind of hard to trust the output that I was getting from the tool because I thought the values were just too high because the wind directions were basically north, especially for our biggest one, the 8.5 tide on that Sunday morning. I think the tool was within like 0.07 that morning. And I remember looking at it and was just very surprised and didn't expect the tide to get nearly that high because I thought the wind directions were not, you know, totally ideal. But we've had some kind of internal deliberation about this. And I think, you know, by that point, there was some impact from just the air pressure component with the surface low being offshore. And I think at some point we just got to where there was so much water kind of trapped in the tidal system that just didn't have time to completely empty out. That was one thing that was driving the tidal departure so high, despite the fact that, you know, maybe the wind directions weren't completely ideal. So looking back, you know, I think in a lot of ways, some of the bigger tides that we had were actually, were more truly like a persistence forecast than we were able to identify in real time.
Yeah, and I also want to make a point to the group, since they're probably not aware of all the data, but this was an extremely challenging event since the guidance was kind of pretty crappy for a couple of runs where it was showing tide levels that were just higher than like some of our tropical events. That was where I really saw the value of humans interacting with the total water forecast to hold their ground and keep some sort of stability on the forecast. Not to say we didn't have trouble coming out of it as well, because coming out of these big extreme events is difficult too. Like how quickly do you lower the tides? Is the guidance right? You know, there's so many things going in. And to Jordan's point with wind speed and direction, and I also think about fetch length, all of that. How much is that? How important is it? How do we quantify that? Are the models good at that? I mean, why was the extra ETSS and probabilistic ETS stuff going so high on a couple of the runs when synoptically the conditions didn't really look that much different? You know, there's a lot of questions in there. So, but we did, I think overall as humans, add value to the forecast.
Yeah, and yeah, I didn't mention that for that recent event, but there were several different runs of whether it was the ETSS or the probabilistic ETSS, where it was giving us forecast tide values of like 11.5 feet at Fort Pulaski. So it was like a foot too high, or a few times where I think the forecast was up around or just over 9 feet at Charleston, which would have put it basically in the territory of some of our recent hurricanes like Matthew and Tropical Storm Irma. And I think my hypothesis as far as why those model sources were so bad at times was because I'm not sure if they're able to assign when the peak departure is actually going to occur. So there were a lot of times where you might be able to see this on the let me go back into present mode here. But if you look at these two graphs here for Charleston and Pulaski, you can see the purple line is the tide departure. So you can see it kind of peaks, hits its minimum just before high tide, and then that departure grows rapidly and reaches its peak sometime before you go into the next low tide. So I think what the model data might be doing is it might be assigning this peak departure. So say at Charleston, maybe like 2.5 feet. It might be actually assigning that right at the astronomical high tide. And if you do that, then you can get some values, of 9 to 9.5 feet. And so maybe the model data is not able to accurately depict, when the peak departure is going to occur relative to the actual tide cycle. That's just kind of a hypothesis, though.
Okay, really good questions and really good conversation. Eric, thank you for being patient. I see you have your hand raised. Go ahead.
Yeah, and I think this actually might be a question for both Blair and Neil, and a little bit off topic, but also kind of related. So kind of when looking over like a season, how much is like sediment transport and like erosion and stuff like that? How much might that impact total water level in the tide, things like that? Is that something that might be a sizable source of error?
I know in some of the papers that I read preparing for my research that, certainly the more shallow the water is, the more responsive the water level is going to become to the passage of ship wakes. So the more dredging that they do, the less potential impacts we should see. But as that erosion takes place, if there's a few years between dredging activities, then maybe we would start to see more and more of a response. But deeper water is usually less responsive.
Yeah, and the only thing I would add is, like Neil said, I think Savannah, at least they're constantly dredging the shipping channel to keep it clear, and so those really large ships can safely make the passage. And in Charleston, they're kind of in the process of actually deepening the channel from 45 feet to 52 feet so that they can accommodate even the largest ships that would call on the East Coast. So I suppose it's possible because neither one of these observation sites is directly over the center of the actual channel. That could be, and I'm not sure. Maybe that's something that the NOS somehow accounts for with how when they go in, like for instance on the charts here, the red line is the observed, and so that's all preliminary data. So what they do is at the end of the month they go back and they go through some process of actually verifying the data, and that's what essentially goes into the long-term record. So I don't know if that's in some cases where they when they verify it, if they go in and account for maybe changes in the deposition underneath of where the site is. I'm not totally sure.
Okay, thanks for your input.
Okay. Any other questions for Blair and or Neil this morning? Okay, I'm hearing none. So with that said, Blair and Neil, thank you both for your interesting presentations and really neat content. I think it's a lot of forward-looking tool development for the region, and it'll be really good to see where this goes moving forward. I guess I'll toss it back to Jeff. Do you have any final thoughts on your end before wrapping up?
No, nothing on my end. Great work, guys. Thanks for sharing.
Okay, so this concludes this edition of the Science Sharing webinar. This will be uploaded to the Eastern Region SSD Google site within the recently shared webinars, probably by later today or tomorrow, depending on time. And thank you everyone for your attendance, and thank you again, Blair and Neil, for your talks. And I wish everyone a great rest of their day. Take care.